Okay, let's continue for section one for the SN diagram and endurance limit. That what I mentioned to you just a while ago, anyway. That what for the external loading just apply to the workpiece. So for the loading change with time or the load is not constant, so therefore we cannot be able to use a sigma y as our reference anymore. So therefore we got to find any other reference for the our designs anyway. So therefore the things that what we're gonna consider based on the experiment that what we call SN diagram, then what we obtained gonna use it is gonna be endurance limit anyway. Then what is said in here, then what I would like to read it out for you guys here. He said here, okay, is that endurance strength rather than the used or ultimate strength is typically used as a basis for the design of machines competence subject to either repeat or fluctuating loading. That's what I mentioned earlier anyway. The endurance strength is sigma n can be determined from the endurance limits of sigma n prime. So therefore, first thing first, we got to find the n sigma n prime, and then we gotta use the sigma n prime to determine the sigma n that we're gonna use for the reference anyway. Let me see. Sigma n prime is the endurance limit or the fatigue limit, of course. So it said in here, the endurance limit, I put the bold letters here. It said here, it's on the experiment. The endurance limit or fatigue limit, sigma n prime, is the maximum reward stress induced in the police test specimen with the diameters of 8 millimeter under unlimited stress cycle without failure. It's the keywords. We have three keywords together. One, it's gonna be the maximum reverse stress, okay? And then second is gonna be Polish test specimen. And third is gonna be the diameter of 8 millimeter of the test specimen. So therefore, in order to obtain a sigma n prime, we got to make a test specimen look like that. Okay, in a three-dimensional form, and then we got to do some the two-dimensional form look like that with an 8 millimeter should look like that. Okay, this is the keywords that what I just tried to show you on here, and then we put this kind of test specimen with a polished test specimen. So therefore we just put this kind of test specimen, we do just grind it and then we just polish it. Okay, so therefore everything's going to be perfect manner with the polished test specimen. Okay, so therefore the workpiece got to be a polished test specimen already. So and then we put it up here on the machine testing or fatigue testing machine. Okay, we have a bearing. We put the test specimen all the way in here, and then the test specimen is in there. We have a collar there. We put a load in there. We put a weight on it, so the collar won't move. Okay, it's allowed the movement only. The axis of the shaft is going to be loaded all the way, and the bearing is stand still. The collar stands still. Okay, the shaft is allowed to move along its own axis all the way. So therefore, this is connected to the revolution counter there. So it's going to count on the revolution. And then we applied a motor to drive it, and we make a counter on the revolution. Okay, and then we apply the weight on it. Okay, so therefore, if we just make a free body diagram, the build over to gonna act on it here, and then another the build over to act on it here. Okay, so we're gonna have a bending loading applied to the workpiece here. So therefore, of course, okay, we're gonna have the build over to acting on here, the build over to acting on here. So therefore, see, we're gonna cause a reverse bending here. Okay, at the top parts, okay, we're gonna have a bending like that. So the top part is gonna be compressive, and the bottom part is gonna be under the. I'm sorry, the top part is gonna be under the compressive, and the down under is gonna be tensile all the way. So therefore, this kind of thing is gonna cause a graph look like a reverse stress look like that. Okay, so therefore, okay, if we just turn from 0 degree to 180 degree, it's gonna turn upside down. The top surface gonna be down under, so therefore it's gonna switch back and forth. So therefore, the stress is going to switch to be positive to be negative automatically. So therefore, this kind of thing, they're what we call reverse stress. So therefore, the stress is going to be positive and negative. So therefore, this kind of thing is we call it reverse stress. Okay, it's going to be pull up and down, things like that. Okay, so therefore, this kind of thing is going to course that what we call the fatigue testing device. Okay, so this kind of thing we're gonna course. Okay, put this kind of testing machine there, and then okay, we're gonna put this on a graph look like that, the axis of y. We're gonna put a strain gauge to take a measurement on the sigma, the stress on the surface here, the workpiece there. Okay, in the axis of y, axis of x, we're gonna have a cycle, number of revolution, of course, in a log paper. Okay, so the graph there is gonna have a plot look like that. It's gonna bend down all the way up to a certain state line there. You're gonna have the sigma n. That what we waiting for. Those kind of thing. The sigma n is gonna be the thing that what we gonna have a constant steer. That what we gonna use is as the fatigue limits or endurance limit. That what we want to have it here. Okay, this kind of graph is going to be the under experiment here. That what I would like you guys to pay attention with this anyway. See, the up to 10 to the third here is going to be low cycle. Any damage, any crack just happen here on a low cycle. That what we have a low cycle. Much material like some kind like couple, things like that. Okay, the couple is going to be some kind of like down under because that's why you see it's not we stand for the fatigue loading at all. For the high cycle, just more than 10 to the third, things like that. For the high cycle, things like that. And then for the finite life, see, 10 to 0, okay, up to 10 to the seventh, things like that. Okay, this is kind of for finite life. So, but nowadays, see, we just consider to be the infinite life, things like that. Okay, you're gonna get started from the 10 to the power of sixth, okay, up to more things like that. So, for the machine design, we just consider highlighted, please. See, if we design machine to meet the 10 to the power of 6, things like that, for the ISO, things like that, meet the requirement. We just define it to be the infinite life already. Okay, but see, you may figure out we have some kind of like overlapping between finite and infinite life. Okay, 10 to the 6 and 10 to the 7th. Some of the controversy between 10 to the 6 and 10 to the 7, between the ISO and to the German DIN, things like that. Sometimes like a controversy between the infinite life and in for the finite life, things like that. Okay, for the standard, maybe some standard is gonna go for higher standards, like 10 to the power 7, things like that, rather than 10 to the power 6, things like that. Okay. So, but for the normal machine design, we just made the requirement of 10 to the power 6. Sorry. Okay. So we, in conclusion, we just meet for 10 to the power 6 for the IO standards anyway. Okay. So this kind of thing. So we just call it finite life up to 10 to the power 6, things like that. So therefore, in conclusion, okay, so if you compare to the tables of the module, typically, okay, we're gonna have sigma n is about to be 0.5 sigma u. If the sigma u is less than 1,400, if it's gonna be greater than 1,400, sigma n prime is gonna be 690, okay, in meter square, things like that. Okay? For the general manual, okay, for the cast iron, we're gonna use sigma n prime is 0.4 sigma respectively. For the magnesium alloy, 0.38 sigma u. For the aluminum, it's going to be 0.16, and then for rough aluminums, 0.38, and for the nickel alloy and copper alloy, 0.45 respectively. Okay, so therefore this one is for the ductile material. We're going to use this, okay, as a reference all the way. Okay, so therefore we got a sigma n prime already. So therefore now, see, for the reality, we're going to use for the endurance strength of sigma n. The sigma n just apply to all. It's because that's why, see, for the standard thing, for the real thing, the surface is not a polished test specimen. Anyway, the size is not 8 millimeter, okay, and the load is not exact. The bending on the way, it might be tension, compression, it might be torsion, whatever. So therefore, if it's not rather than the standard things that what we talked about before, see, if it ground surface, okay, things like that, we're gonna go for 0.98 89, okay, for the ground surface. For the machine, a chrome down surface, okay, 0.84, things like that for the hot roll surface and a forge surface, things like that, okay. And for the size modification factor, okay, gonna be 1 if less than 8, okay. And then for the size of the shaft, it's gonna be 8, between 8 and 50, okay, 0.85. And then if greater than 50, it's going to be 0.75. I want you guys to highlight it is here. Typically, the size of the shaft, okay, with the normal size of the shaft is going to be in between 8 to 50 millimeters all the way, okay. And then be careful if I said here, okay, if the design machine doesn't have a circular cross section area, the size modification KB K sub B has to be from the smallest, okay. So it's dimensions of the cross-sectional area, of course. Okay. And then K sub C is going to be 1 for bending all the way. If the combined loading, if bending is associated, okay, use 1 all the way. Okay. Compressive and tensile 0.8 and then torsion 0.6. And then stress concentration, I just talked about it already. Okay, K sub D is right there, okay, at the each of the graph, at the appendix 3, at the end of the chapter, at the end of the textbooks anyway, okay? And then the things that gonna be wrapped up together, the two things together, okay? Remember on the beginning of the lecture that what I mentioned for the load change of time and then together with the stress concentration, it's gonna be happening right there. We're gonna just pinpoint the most likely failure going to be right there at the stress concentration area, most likely failure. And then, therefore, we're going to use the endurance strength as a determination for the design anyway. So, therefore, in order to do on this, we're going to use a Soderberg criteria to do on it anyway. The Soderberg going to be look like that. The Soderberg can be classified the stress to change with time with a fluctuating stress, repeated stress, and reversible stress, respectively. In figure A, you may figure out, see, everything can be positive all the way. We have 4 sigma all the way. See, we have a sigma max, sigma min, sigma amplitude, sigma means is going to be all positive all the way. Okay, and a repeated load, sigma min is equal to 0 rather than that it's going to be positive all the way. Reverse stress, okay, it's going to be maximum going to be positive, minimum is going to be negative, and the mean is going to be 0, okay. The amplitude is going to be the wavelength anyway, okay. So therefore, everything's right there. It's going to show you up the equation that what you look like. The amplitude is going to be max minus min over 2. The mean is going to be max plus min over 2, respectively. On each of the corresponding sigma A is going to have F over A, M times C over I, and then tau is going to be torque times R over J, things like that. Okay, M times C over M times C over J, things like that. I'm sorry, M times C over I, respectively. Okay, and then for the Soderberg, for the sigma all the way, is 1 over n, and sigma m over sigma I, and k sub t is sigma a over sigma n is 451. For the ductile material, see, we have a sigma y all the way, and then vitro we have a sigma u all the way. Okay, for the shear eroding we have only tau, so therefore everything's going to be changed to be tau. And this keep careful, tau sub y is equal to 0.6. This is going to be simple stress, right? Because that's why we all have only one stress available there. So therefore, this is K sub T and K sub T sub S. That's what I mentioned, only simple stress. Okay, let's have a look at it. First example, respectively. In the first example there, an AISI 1020 HR steel plate have a ground surface and subject to the fluctuating stress value from 0 to 20 kilonewtons to mean the steel plate thickness by using safety factor n is equal to 2 and son of a kite. So have a look at it, okay? We have a plate there, so that's why we have a F there. We have an arrow, no? For external force, we have two arrow. It's mean, okay? The load have changed with time. Be careful here, okay? F, that mean this kind of thing. The F is such constant. Is the F here is going to change with time. So therefore, okay, if just like this, okay, I just look up in appendix number 1, sigma y is 210, sigma u is 280. So therefore, just based on the sigma u is less than 1400, I find the sigma in is 0.5 sigma u based on here, right? On page number 4, on page number 4 there, right? Yeah, right? Left natural. Okay, you says that at 1,400 sigma n prime is 0.5 sigma u respectively. So therefore, I come back here at the example. I find sigma n prime. Okay, and the steel plate for a ground surface, K sub a 0.89 is given. Okay, so ground surface. So therefore, I found the ground surface K sub a ground surface, okay, 0.89, is that right? Ground surface, okay. So therefore, I got it here. I got it here. So therefore, assume that the thickness is less than 8. The reason, because that's why I see typically the steel plate is typically thicker than 8 millimeter. It's going to be very thick already. So that's why I assume to be for the reality, it's going to less than 8 millimeters. Okay, so that's why made foam, page number 5 there, page number 5 there. Okay, sub C is okay, is less than uh, sorry. K sub B is in between, right? 8 to 50. Okay, use the thickness, right? So therefore 0.85. Okay, so therefore I find it, okay, K sub B, and then compression and tension, K sub C is 0.8 based on those kind of things. So that's why I find a sigma n respectively, and then I just look up in the graph D and W, right? I just use the appendix 3 and then D sub W, D O W, and then I look up the graph and K sub T there. So that's why FM, FA, okay. I got FA and FM, and then I got the sigma M and sigma A. I plug it in and solve the criterion. I got T is 11. Since I assume here T is less than 8, so that's why my assumption is wrong. It's wrong. So that's why I just get back there. I make a recalculation. I just get the K sub C, K sub B one more time again. Gonna be 0.85. So I got the real calculation. It's gonna be 12.56. Okay, and why? So this is the thing that what I gonna go for it. Okay. So therefore, this is the answer. Okay. All right.